Okay, so welcome to today's project presentation of first year students who are doing their coursework. So today we'll have three talks, and the rule is that this is like 25 plus 5 minutes talk. So each student will give a talk of 25 minutes, followed by 5 minutes of question answer session. But you are allowed to ask questions during his talk as well. Okay, so let's begin with Rahul. Okay, so Rahul, your time starts now. You can share your screen and begin your talk.
Okay, I hope I'm audible clearly.
Yeah.
Okay, great. Good afternoon, everyone. So today I'll be discussing whether the universe is confused. And that might sound strange at first, and it is strange. Is the universe confused? It should not be. If it is, then the study of the universe itself is meaningless, and there's no point in exploring the cosmos. If we assume it is not, then certainly we are confused. And the source of this confusion is the topic of my talk today, and this is popularly called the problem of the Hubble tension among cosmologists today. So this is the broad overview of the message that I'll be trying to convey to you over the next 20 or so minutes. What we are trying to do is trying to build a bridge from the early universe to the late universe and vice versa. But you'll notice from this graphic that there's a problem with this bridge. There's a gap. I mean, it doesn't quite join up in the middle. So this is dangerous. So we'll try to understand why this happens and what could be the possible solutions to this. So in order to even try to solve this problem, or we need to understand the problem. And in order to understand the problem, we have to go right back to where cosmology started. So, before 1924, people used to think the universe is static. There are some stars around us, and then beyond them, there are more stars, and beyond them, there are merely many gas clouds which have more star-forming regions. But Edwin Hubble was somehow the right person because he was definitely a genius, and he was at the right place, the Mount Wilson Observatory, and it was the right time also because the technology was at a stage where he was able to do what he did. So what he did was he tried to observe beyond these stars and beyond these gas clouds, and he observed that there exist galaxies beyond our own. I mean, there exist complex structures beyond our own Milky Way, and that was very, very surprising. But what was more surprising was found later after he worked on these objects and discovered many more things after 5 or 6 years. What he did was, in particular, he studied something called Cepheid variables. So, certain stars, these have certain these have definite time periods of pulsation. So by studying these time periods, you can actually deduce how far they are from away from us. So if you take a certain Cepheid variable, you can find the distance to it. And if you do a spectroscopic study of the light that's coming to us from that source, you can also find the redshift. And of course, if we know the redshift, we know how fast it's moving away or towards us, the velocity. So what Hubble did, he plotted this. He plotted the distance versus the velocity of these objects. And he found something very surprising. He saw there's roughly a linear relationship. Of course, it's not exactly linear. There are many fluctuations about the straight line, but it's roughly linear. So he gave this empirical formula, which we today know as the Hubble's law, and it basically means that the farther away an object is from us, it's moving that much faster away from us. And this is surprising. I mean, this cannot happen in a static universe, and this was revolutionary. And at the same time, there were people like Alexander Friedman and Georges Lemaitre who were extremely ambitious, and they said, okay, there's this new fancy theory called general relativity. Let's apply this to the whole universe. And they did so. And surprisingly, they found that a non-static universe, probably with even a curvature, is not an unphysical scenario. It can be possible. And this was a very, very strong support for Hubble's recent discovery. So over the next few years, or rather next 50, 60, 70, 100 years, many observational and theoretical developments took place. And at the end of it, we reached something called the standard cosmological model. This model basically takes in 6 parameters, or rather 6 numbers. If you're able to provide these 6 numbers, they will uniquely determine the complete absolute evolution of the universe. And that is insane. I mean, you have just 6 numbers to say everything about the universe from its birth to the end. So this model has been very, very successful in explaining almost everything we throw at it, almost every cosmological observation we throw at it. However, of late, especially since it's an age of precision cosmology, you are reducing your error bars beyond, to a level that is unprecedented till today. There are certain problems cropping up, and the measurement of the Hubble constant is one such major problem. But before I go into the problem, you might ask, okay, the Hubble constant is some number. So what? Who cares? It's just one number that we can't measure. We can measure other things. Not really. It's like I have to say the Hubble constant measures the current expansion rate. So let's say you live in a house which has a house which you cannot escape due to the cosmic speed limit. And this house, the ceilings, the floors, and the walls of it, they move away from you. And if you're living in this house, you want to know how fast these things are expanding. If you don't, that's weird, but you have to know it. So that's a very qualitative argument. But on the quantitative side, if you have a theory, if you have a model like the lambda CDM model, and if you have a hold on other constraints from other experiments, the Hubble constant, the H naught, if you see this complicated expression here, if you know the H naught, you can actually, in principle, know the expansion history at different redshifts, or rather at different eras of the universe. So the H naught is very, very central to the whole of cosmology. It helps you know the age of the universe. It helps you know how much dark matter is there, how much matter is there, of course, correlating it with other data sets, and so on and so forth. So it's really, really central to knowing about our universe.
Sorry,
Also, as I
Rahul,
said,
this H naught
yes,
is the current value of the Hubble constant?
yes, it is. So
That's
we define Hubble parameter as a dot by a, where a is the scale factor. So this can be defined at any time or at any redshift. So what we are trying to measure is its present value. The
okay.
farther you look, that's in the back. So you're trying to measure the present value.
I see. Thank you.
Also, yeah. So as I mentioned, I was mentioning the standard model, the lambda CDM model. A correct measurement, a precise measurement of H naught is also serves also as a test for lambda CDM. Like you have a model which is trying to, explain the evolution of the universe. So if you measure it, let's say from the late universe, and you measure something from the early universe, and they match up, that means lambda CDM is correct, because I must mention some of these measurements that we do, these are model dependent. So let's say you have a model independent measurement, you get some value, you do a model dependent measurement, you get some value. If they match up, okay, lambda CDM is great. If not, there's a problem. So this is also a very, very good test for the lambda CDM model, and hence the need to know a good value for H naught. Okay, so we know what H naught is. We know why. I hope we understand why we need an accurate value of it. So there have been different probes to measure it. One, obviously, what Hubble did, we can do it in a better way. We can observe more objects, measure their velocity and distances more accurately, draw a straight line, find its slope, and get the Hubble constant. Or we can use something called the CMB, which is like the light emitted by the universe when it was just a baby, merely 380,000 years old, compared to its 14 billion years of age today. So these are the two broad categories of measurement probes that we have. But before I go into the specific probes, these are the two main principles that we use. The luminosity distance, like you take a standard candle, you put it at a distance, see how much bright it looks, and by the inverse square law, you can estimate how far it is. Or you can take a standard ruler, say a meter scale, for example, and you put it at a distance. Obviously, it appears shorter to you. How much shorter it appears will also give you an idea as to how far it is. So these two basic principles are mostly used. And the first method, that is merely an improvement of Hubble's method, was using the luminosity method, luminosity distance method. So in this, what we do is we take some nearby objects, stars or something, and you try to measure the distances to them through geometric methods, not luminosity distance method, through geometric methods, like using parallax measurements and all, because you know the Earth goes around the sun, there'll be changes in the angle of that object with respect to the background. So you measure these distances, and then you take those as the base values, and then try to calibrate distances to farther away objects, such as Cepheid variables, as was done by Hubble. And those variables then, after they are calibrated, their distances are calibrated with respect to their pulsation period, then I can use those as my base and calibrate even farther and more brighter objects, such as type 1 supernovae. And people have done this, and of course, unsurprisingly, you get a straight line, and you compute the slope. And the present value of H naught using this measurement is roughly 74 plus minus the error 1.4. Now this 74 is very important. I would like you to remember this value. I'll come back to that in a moment. Okay, so this is lensing. This is just another method of measuring the Hubble constant in the late time universe. I mean, you can observe lensed images of galaxies and stars and see and calculate the time delay between the appearance and disappearance of the images. And then doing some complicated mathematics and computation, you can also deduce the expansion rate. And unsurprisingly, this also gives a very, very consistent value with the previous method, about 73.3. Excuse me, plus minus 1.7. So it's near about 74, so to say. And these are just some more late universe measurements, which the details of which I'll not go into. But what is important is they're all quite consistent. It's about 73, 75, 73, and so on and so forth. Okay, so late time measurements are pretty consistent. Great. What about early time measurements? So we go to the CMB, and if you just skip these complicated graphs and these colorful graphs, you see this value is about 67.4, and that is surprising because this is very low. It's and even if you take the error bars into account, this is still quite low. But I'll come to the disparity in a moment. Before that, I'll just try to give you an idea how we get the value of H naught from the CMB. I mean, if you have a model, that model will tell you, I mean, you're assuming a model, I mean, so that model will tell you what was the possible constituents of the universe at the time of recombination, or as we say, the CMB. And that tells you what is the distance a typical sound wave travels in a certain time. And this distance is called the sound horizon, or RS. So if you know RS, and if I calculate that angular difference on the CMB sky, I can calculate the Hubble constant. Of course, it involves some formula and some calculations. Again, the details of which I'll not go into, but you have to realize this involves the method of standard rulers. I was talking about standard candles, and this is what we use as standard rulers. One more interesting thing of standard rulers and the sound horizon is that I say sound waves. Sound waves are longitudinal waves, which means there are compressions and rarefactions in the medium. So in a gravitationally interacting universe, if there are compressions, that means that's overdensity, and overdensities will grow over time, and underdensities will reduce, I mean, get rarer over time due to gravitational interactions. So can we see this later? Can this initial, I mean, image of these sound waves, I mean, travel in the late universe? Yes, if we do galaxy surveys, we do see certain overdensities and densities, and these can also be used to, I mean, measure the Hubble constant in the same principle, but at different redshifts. So this is what we call the baryon acoustic oscillations at different redshifts. So this is also an alternative method to measure from the CMB, and this also gives a value consistent with the CMB, about 67.3 or so. Okay, so now coming to the problem. Late time measurements, about 73, 74. Early time measurements, 67. They don't match up. How do they not match up? They don't match up up till about 4.54 sigma. Like, and sometimes even 6 sigma. Like if I take the average to be 5 sigma is considered a golden standard in particle physics for a new discovery. So you can well understand how unlikely it is that, I mean, these values to be different if it should not be different. So there is a problem. There is definitely a tension. And this is just another graphic to show you. I would like to like you to focus only on the first row here, which is the Planck results compared to many different late time probes. I mean, why Planck? Because that is like the most accurate, I mean, most high resolution observations we have from the early universe, and they have tensions about 5.7, 5.26, and this is bad. I mean, it's really, really bad. This tension should not be there. Also, this is just a side note. You might have noticed here, like they mention like WMAP plus BAO, this plus that, this without that. This just means combining data sets. I mean, we are doing different probes. We are using different probes to get different values, but sometimes you also have to combine data sets. Why? Because let's say I have 4 quadrants. For example, on a 2D plane, I have 4 quadrants, and my value of H naught is, let's say, in the second quadrant. I do an experiment. It tells me it's in the upper half or the lower half. If it tells me it's in the upper half, great, but I don't know which quadrant it is in. So I do another experiment, and that tells me it's in the left-hand side of the plane. So then I know it's in the upper. So in this way, we combine data sets to, I mean, constrain our cosmological parameters in the better way. Anyway, this was just a side note. This is another graphic. I'm sure you cannot read any of this text here, but what is important is I hope you can see this pinkish bar here and this bluish bar here. This pink bar is roughly the average value of every early time measurement we have done, and the blue one is roughly the average value of every late time measurement we have done. Surely these do not match, so there is definitely a problem. Okay, so there is a tension. Something is not matching up. So does that mean cosmology has fallen apart? Is everything over? Nothing to do? We hope not. Definitely, we hope not. Actually, it's quite the contrary. This tension has arisen not because of our laziness to measure or our inability to measure something or like that, but it's mainly because we have been able to reduce our errors to such an extent that we see this disparity. It's almost like if you know about Mercury the precession of Mercury's orbit. I mean, that's a minuscule effect. Who cares? Doesn't matter. But the efforts to solve that led ultimately to the GPS systems that we have. Imagine having a life without GPS systems today. So that's what makes this interesting. And in this era of precision cosmology, definitely hints this problem definitely hints at new physics yet to be discovered. Okay, so there's a problem. How do we go about solving it? Two things. First, we are assuming lambda CDM. Maybe it's not correct. Maybe we need some extensions. So there has to be some theoretical modification. Two, maybe the theory is okay, but somebody is doing the experiment incorrectly. Systematic errors. So I'll first talk a little bit about the theoretical efforts that have been made. Unfortunately, since we are trying to model the entire universe and we are trying to extend a model which is so consistent with every other observation, whenever you try to tweak anything in the model, it runs into problems with other data sets. Like you are trying to resolve the H0 tension, maybe you're successful, but something else goes worse, like the sigmoid tension or so on and so forth. Even some people have commented that if you extend your model, you see that even under that extension, lambda CDM is preferred, so to say. So nobody has been able to find a, satisfactory extension to this model. In fact, as I was saying, when you measure the Hubble constant from the CMB, you have to assume a model. And if you extended this lambda CDM model with some external parameters, the tension becomes worse. I mean, the values decrease. If you see this value 65, so 65.9, 63.6, it should increase because I want to put these values nearer 74 or so. So it makes the problem worse. So now you realize how serious this is. There are some other modifications which do try to increase the value, but still, if you see, they are not quite there yet. There's still room to decrease the tension. And of course, you might ask, let's just push it a little bit more, but you cannot, because the moment you do that, it, as I said, runs into constraints with other data sets. Okay, so somewhere down the line, some people conjecture that, let's say, okay, we observe a higher value of H0 in the late time. Maybe something funny is happening in the late universe, because of which we are observing a higher rate of expansion right now. So many people had put forth many modifications to the theory, like phantom dark energy, phase transitions, so on and so forth. These were okay. They were all right to explain this tension to a certain extent. But you have to realize, if I am modifying late time physics, it has to be consistent with late time observations. And why do I trust late time observations so much more? Because late time observations is late time. I mean, they are closer to me. It's easier to get a handle on those rather than something that was about 11 or 12 billion years ago. So unfortunately, any late time physics modification runs into problems with late time observations. So maybe it's not late time. So let's go to the early time modifications. Remember, I was talking about the RS, the sound horizon, the standard ruler on the CMB. It has been shown that if you reduce RS by about 7%, you can resolve the Hubble tension. So people try to do that, this and that, and ultimately, Zadamjic et al. And their group, in 2020, they showed that even if you are able to reduce RS by 7% by doing some modification to your theory, you cannot resolve the tension without running into constraints with present data sets. So again, this is a dead end. There were many more models introduced or proposed, but many of these models either failed or they require more higher resolution observations from the early time universe, which we still do not have, and we hope we will soon have. So on the theoretical side, it is more likely that a modification in the early time physics would probably solve this problem rather than uh, some uh, some new physics happening in the late time universe. Okay, so I was saying about the theoretical advancements. How about somebody's doing the experiments wrong? Theoreticians love to blame experimentalists, like you're not doing this wrong, that wrong. My theory is correct. You're observing incorrectly. But unfortunately, any group that does an experiment, that those results are always cross-checked hundreds and hundreds of times by other groups. And till today, whatever systematic errors have been found, they are not enough to explain this problem, this disparity in the measurement. So maybe statistical errors. Maybe we do not have enough data. Maybe we are trying to, for example, fit a fourth order polynomial with 3 points. That's absurd. I mean, so maybe we need more data naturally, or maybe there are degeneracies, and there are some degeneracies. By degeneracies, I mean, say you have a physical system. There are two parameters in it, A and B. If you change A, the physical system changes. If you change B, the physical system changes. So if you observe a change in the physical system, how do you know whether A changed or B changed? So for this, we need newer probes so that we can somehow study a system by fixing A and changing B and so on and so forth. So these are what we call degeneracies in cosmology. So yeah, this is what I was trying to say. We need more data and we need newer ways to measure. Also, it was shown in 2018 that there exists a positive correlation between the H0 values and the sigma 8 values. I mean, if you try to constrain H0, I mean, if you try to reduce the tension in H0, sigma 8 tension gets worse, and vice versa. And this was generic to present data, which means we need more data. Okay, so these are my conclusions that there is a problem. It's undeniable. Of course, if it's not a systematic error, and we need better probes, more expansive data sets, and so on. And these are some of the future missions that are in store. Sorry. So what is important about these future missions is there are two kinds of future missions. One, it tries to expand on current probes. Let's say CMB. CMB, as measured by Planck, is the highest resolution we have till today. But what about more higher resolution? Only then we can test newer theories, disprove or prove them. I mean, accept them. And the other thing is we need absolutely independent probes, especially at higher redshifts, especially towards the middle of the bridge that I was talking about. We are trying to build a bridge and it's broken in the middle. So if we can measure directly some probe which probes directly towards the middle of the bridge, we'll probably know what's wrong or what different is happening. So examples of those are the 21 centimeter signal and of course, gravitational waves. 21 centimeter signal is inherently high redshift, but gravitational waves is not inherently high redshift, but it has the ability. I mean, we have the ability to probe higher redshifts with gravitational waves.
Rahul,
Yeah.
sorry, you have 2 more minutes.
Thank you. I'll finish it up. Okay, this is a technical slide. I'll probably go through this very quickly. This is a technique in statistics called Fisher forecasting method. If you know your experimental setup and if you know your priors or your expected values, prior expected values on your parameters, if you put those into this mathematical constant, it will give you a handle on with how much precision you can obtain new constraints using your future data. In a sense. So this method is often used to better your future missions, to tweak your models, and so on and so forth. Anyway, I'll just skip through that quickly. Yeah. So I was talking about independent probes and higher redshift probes. Out of these, gravitational waves is something which particularly interests me. Why? Because not only for H0 tension and not only for cosmology, but astrophysics and astronomy as a whole, GW is a completely new window into a universe, and because still today astronomers were completely limited by the electromagnetic spectrum. Moreover, GWs travel unimpeded, I mean relatively unimpeded compared to electromagnetic waves. So you can observe these events at higher redshifts compared to, as I said, optical observations. So this is a very promising, promising probe in the future for intermediate redshift, but there are problems in the sense there are too few detectors right now. There are not many data points to constrain H0 to a satisfactory level. Also, I'm sure you know that just for discovering gravitational waves, there was extreme technology involved. So now we are trying to do precision cosmology using this. So extreme detector calibration is required. Then there are problems of degeneracies, and then there's a problem of simultaneous optical and GW observations. But we hope as the technology improves, and as we get more and more data, we'll be able to work around them. So yeah, there's a problem. New physics is probably required. If not, we need newer probes, and only then probably we'll be able to come in on this issue. So initially, when I thought about I'd heard about this problem. I was like, okay, there's some value which we can't measure. Maybe we are doing something wrong. Something must be wrong somewhere. But then I slowly realized that no, this has so many interrelationships, so many caveats with so many other things. I mean, it almost relates everything in cosmology. And over the past few months, I've only just barely touched the tip of the iceberg. And I hope, I really want to explore this subject a little bit more. And maybe not, I cannot hope to solve this problem ever, but maybe I can give my insight to this sometime in the future. So that's it from me. I would like to thank my advisor, Professor Supratik Pal, for his continued guidance. Without him, I would not have understood half of this. And my peers with heated discussions with whom helped me clear many of the concepts that were required to understand this. So thank you. I will now try to answer some questions if there are any.
Okay, so thank you, Rahul, for a nice talk. Time for some quick questions, maybe from the audience. Those who have joined online or from those who are here.
Hi, Rahul, just a short question. Like you mentioned briefly that Jadamzik showed there were some problems with this reduction by 7%, right? Like,
yeah.
I just got a bit lost. Like, how did they manage to reduce the RS by 7%? Can you just remind me?
No, so they are saying any other people had said that if you are somehow able to reduce RS, you will be able to resolve the tension. But then Jadamzik showed by analyzing different data sets that even if you are able to do that, there is some of the other data set, some observation that will always run into an inconsistency. I mean, whatever probes you presently have, you cannot keep all of them consistent and reduce RS to resolve the Hubble tension. This is what they ultimately showed.
I see. So there is no exact explanation of how to reduce RS by 7%.
Using, of course, you can always cook up fancy theories, but even if you have theories, you need more data. Hence, my focus. I mean, my insistence that you need more data, you need more independent probes to test those theories out. What Jadamzik is saying is not that you cannot reduce RS. They are saying that with current data, you cannot solve this problem.
I see.
That is what it is.